I'm Bob Agnetti. I'm with NASA Marshall down in Huntsville, Alabama. I've been working there in the field of environmental control and life support my entire 27-year career. Before I moved to Alabama, I grew up here in Massachusetts, and based on what I just saw, things have really changed up here since I've been gone. I don't remember us ever doing that back, but hey, go for it. I'm really glad to get a chance to participate in this workshop. I honestly think, and I'm not just saying this because I'm trying to be politically correct, I honestly think one of the more important things, or probably the most important thing that we at NASA do, is try to inspire. I think that's what we're all about. That's what exploration is. And to get people like yourselves involved in what we're doing, and to share with you some of the challenges. I hope we're able to get a little bit of inspiration into you. So I think it's a great field. I am just so totally thrilled that I had the lucky opportunity to enter into it when I did. So I'm a chemical engineer by training in the field of environmental control and life support. That to me is a chemical engineer's dream. I'm much happier doing this than running a refinery or making plastics or something like that. I will not be doing the only person you'll be hearing about talking about environmental control, or ECLS for short. I'm going to start out giving you just a very broad, very top-level summary describing what ECLS is. And then we have a presentation on the historical approach to providing environmental control and life support dating back to the earliest days of the space program. That presentation was prepared by Hank Rotter. He is the NASA Tech Fellow for environmental control and life support and active thermal control. He was going to be here this week. Unfortunately, he got called away and had to travel overseas. So I'll be presenting his material. I hope I can do it justice. And then we're going to have a number of people tying in from a number of different centers, tying in remotely to give you a more detailed discussion on some of the major functional areas that make up an entire ECLS system. Molly Anderson from the Johnson Space Center will be talking to you this morning about what considerations go into conceiving and developing and defining what type of ECLS architecture, what type of system approach makes sense given whatever type of exploration mission you're contemplating, because depending on what the mission parameters are, that can lead you down one of several different paths in choosing how to design your ECLS system. And then over the course of the remaining day and a half, we'll have different what we call subsystem experts going into a lower level, a greater level of detail in certain functional areas. Jay Perry from Marshall will be wrapping up this morning's session talking about air revitalization. We'll break for lunch. Then Jim Bryan from Johnson will be talking about waste management. It's probably good with that fell after lunch rather than before lunch. And then we, following up with the rest of our NASA speakers, tomorrow morning, Daryl Jan from the Jet Propulsion Lab will be talking about spacecraft environmental monitoring. Ray Wheeler from the Kennedy Space Center will be talking about biologically based ECLS processes. And then at 10 o'clock, your schedule has a topic called Stupid Ideas. We're replacing that Stupid Ideas, hopefully, with a not-so-stupid presentation. But Karen Pickering from the Johnson Space Center will be talking to you about water recovery. That was on the original agenda, and we had had to do some reshuffling based on personnel availability, but I'm glad we're able to stick that in there. And then finally, tomorrow afternoon at 2:30, Gary Ruff from the Glenn Research Center will be talking about spacecraft fire safety. So hopefully through the course of all this, you'll get a little bit of appreciation on environmental control and life support, what is involved in that, what it takes to keep people alive in space. Once you're successfully protected from the radiation environment, once you've done that, there's a lot more to keeping them alive and healthy in space. So we hope to give you a flavor of that. So unless there's any questions about the overall plan, we'll get right into it. All right, environmental control and life support. Obviously, our Earth does a heck of a lot for us. It provides for us what, to us, I think sometimes we take for granted. Provides us, obviously, the air to breathe, the water to drink, and the food to eat. And as long as we take care of Earth, which is probably another topic of another innovative challenge workshop, as long as we take care of Earth, Earth does an amazing job giving us everything we need to sustain ourselves. However, we start leaving Earth, we still need air to breathe, water to drink, and food to eat. And that's the challenge. How do we take the functions, how do we provide the functions that we've come to take for granted, in large part, here on Earth, and how do we provide for those functions in as efficient and reliable way as possible as we depart Earth and extend ourselves out into the solar system. So what does it take? What does it take to keep a person alive? Some of it's obvious, some of it's a little less obvious, but what we tend to do, especially when we're in the very early stages of planning life support systems and thinking about what types of resources we're going to have to provide and what type of consumables, one of the very first things we do is we start off with what we call the average human metabolic balance. Right up front, the big qualifier on this is nobody's really average. The people vary a lot physiologically, metabolically. We typically design missions to accommodate people from 5th percentile female to 95th percentile male type of populations. There's a lot of variability. But when you're trying to conceive of in the early stages of trying to conceive a life support system, we typically start with average human metabolic parameters. Basically what that involves is we have to provide a certain number of commodities to keep a person alive, and some of those are pretty obvious. First being oxygen. Sometimes people are surprised by how much oxygen we consume over the course of the day because you're never really thinking about it, but it amounts to close to 2 pounds of oxygen per day. The largest commodity we have to supply by mass is water. Typically, on average, we take in a little under a gallon of water per day. Most of that, almost half of that, we take in directly as we drink either water or coffee, fruit juice, whatever. A portion of the water we also consume the portion of that water in the form of food. Juicy apples, vegetables. A lot of those foods themselves have a fair amount of water content within them that our body uses. And then finally, we consume some water that's associated that we basically add to the food as we cook our pasta or rice, or a lot of that water gets absorbed into the food. We consume that food, and that represents a net input of water to us. And then finally, food itself, the non-water portion of food, a little under 1.5 pounds of food solids, and if you look at the elemental makeup of that, oxygen, hydrogen, carbon, and other, very, very much a carbohydrate-dominated type of diet in general. If you add up what I call all the ins, it turns out that each of us, on average, over the course of a day, is taking in close to 11 pounds of mass over the course of a 24-hour day. Basic, engineering 101, mass balance. What comes in eventually has to come out. Where does it come out? Well, first thing that comes out, well, not the first thing, but the first thing on my list, carbon dioxide. Your body metabolizes the food. It uses that oxygen that you're breathing in to break down the food and oxidize the carbon. You wind up exhaling a little over 2 pounds of carbon dioxide over the course of a day. Water, again, is the major output material. That water comes out a number of places. The obvious one is urine, a little over 3 pounds of urine per day. Maybe less obvious is your sweat and respiration. 24 hours a day, you're breathing. Your breath that's coming out is saturated with water vapor. You notice that very much in the wintertime when you see that cloud of water vapor form in front of your face, but that's obviously there all the time. You also lose a fair amount of water just naturally through your skin as part of evaporative cooling, even when you're not doing tribal war dances like you were just doing. And then finally, there is some water content within your fecal waste. Not a large amount, but there's some there as well. And then finally, solids come out. Some of it comes out in your urine. Not a large amount. Urine is about 97% water on average. A lot of minerals come out in your urine. You get a little bit of mineral loss in your sweat. Then your non-digestibles come out in your fecal matter. So that on average, what comes in comes out. That's kind of what we plan on. This is in the balance we're showing here is for human metabolic purposes. Basically, you can consider this to be the bare essentials for keeping a person alive. Obviously, there are other uses and needs for water, for personal hygiene in particular. That would be those uses, needs for water, and the wastewater that's produced in the course of using that water for those purposes would be over and above these basic human metabolic needs. And that's kind of mission specific. What type of amenities do you want to provide to the crew? What type of amenities can you afford to provide to the crew?
Is it okay to ask questions?
Yeah, please.
So one of the one of the projects that we're looking at right now, separate, we're looking at like in Saudi Arabia, what's the what the infrastructure needs, and the population there is growing, and we have a spreadsheet of number called municipal water withdrawals per capita. So for different countries, and different countries use less than others, but in the United States, it says that the average municipal water withdrawal per person is 573 liters per person per day.
Yeah. That
right? So I'm looking at that number, and then I'm looking at those numbers, and there's like almost 2 orders of magnitude difference.
There's
how do we explain that?
For starters, you and I, or all of us down here, we do things down here on the ground that we don't do in space. We wash our cars, we water our lawns, we flush our toilets many times over the course of a day. We are rather free with our water as we shower. We're probably all guilty of turning the water on, letting it run until it warms up nice and toasty. We tend not to be very conservative in our use of water down here on the ground because of its abundance, among other things. But then there's also, and I don't know exactly where those numbers come from, but a lot of services that we get, clean laundry takes up a lot of water. Restaurants, and as they're out there providing us food, they're washing dishes and a lot of that. So there's a lot of that other stuff, not necessarily associated with keeping us alive, but with keeping us comfortable and happy and maintaining the lifestyles we do down here on Earth. But I have heard, I wasn't familiar with that number, but I've often heard that the United States is among the highest, if not the highest, in per capita water usage. And you hear a lot in the news now. Water wars. I'm from Alabama. Not so much this year, but in a couple of recent years, we had some fairly high drought conditions. Georgia and Alabama share some water sources, and you start hearing about some tensions growing amongst the states about who has the right to use that water, and because of that, and that's probably going to continue to change. Our population is always going to continue to grow. Our fresh water supplies on the planet are basically finite, and I think those tensions are going to continue to grow.
I have a question. These calculations here, are they taking into account the astronauts exercising in space and the amount of exercise?
Yeah, these are daily averages. There's actually a set of parameters like these that are specific for exercise as well, and they tend to be higher. And what we tend to do, and again, this gets into mission planning, is you try to establish early on is exercise going to be a major part of the astronauts' days, and then you account for that, those periods of exercises, 2 to 4 hours.
So if you were to say for 4 hours of exercise, would you increase that number by 20%, or would you say that number is more
in general, not the bottom line number? Your oxygen would go up, your water would go up.
Right. Okay.
Mm-hmm. I was wondering at what stage of the ECLSS design process do the astronauts come in, like with feedback?
We try to get them involved as early as possible. There's been NASA's been doing a lot of very early mission concept design definition, architecture studies. Several years ago, there was quite a bit of effort, detailed studies on different type of lunar exploration scenarios. We had astronaut participants in those as well. So it really helps us out to get them as the ultimate users involved in what we're thinking. All right, good questions. So, no matter what type of spaceship you're designing for the future, there are some basic functions that you need to consider and that you need to provide. The functions that we typically associate with ECLSS, and some people define the functions of ECLSS a little differently than others. Some programs within NASA kind of divide the functions up differently, but in general, these are the kind of functions you would have to provide in any kind of spaceship where you're intending to keep astronauts alive and comfortable. Those include, like you saw in the previous chart, supplying oxygen, removing carbon dioxide. You've probably all seen the Apollo 13 movie. One of the many challenges they had on that return mission was removing the carbon dioxide from the lunar module they were using as lifeboat. If CO2 gets too high, concentration of CO2 gets too high, it becomes a toxic gas. And so a very important function is to remove that carbon dioxide. We have to control the cabin pressure, keep it from getting too high and causing some type of structural failure on the vehicle, or getting too low and causing ill effects on the astronauts themselves. We have to control the cabin atmosphere composition and its purity. And by that I mean we have to maintain the proper balance of oxygen and other gases, typically nitrogen, in the cabin atmosphere. We also, in any type of closed environment, we have to pay particular attention to what we call trace contaminant buildup in the cabin. Everybody has had an experience where you've gotten into a new car, you get that new car smell, but particularly is the car sits for a while. Sometimes you see that buildup of film inside your windshield. Well, all that's coming from what you're smelling and what you're seeing. The film buildup on the inside of your windshield is of volatile organics. They're coming off the materials of construction of the car. Some contaminants coming off of you as you're riding in your car. And if your car were perfectly sealed, over time that could wind up leading to some physiological problems for yourselves. Obviously, your car's not sealed. You're opening the door. You're driving with the windows down, so it's not a problem. But if you have a sealed spacecraft, those types of phenomena continue to happen, and so it becomes very important for us to actively control and remove those impurities from the cabin atmosphere. We have to control the temperature, humidity, and particulates down here on the ground. If you're not a real great house cleaner, you notice over time you get dust buildup on your furniture, and a little bit of a hassle. But in space, in the absence of gravity, those particulates don't settle; they stay in the atmosphere, and you can wind up causing some respiratory problems. So you've probably all had to clean your air conditioning filters at one time. That's actually quite a large challenge for us in orbit. Space station guys, Charlie can probably attest to this, spend a lot of time housekeeping and cleaning debris off of cabin filters. We typically have to make sure we are ready and able to respond to and recover for environmental emergencies, whether they be fires or the aftermath of fires or the aftermath of some type of spill in the environment. We have to ventilate the cabin. Down here on the ground where we have gravity available to us, if we turned off all ventilation in this room and shut the doors, there would still be natural convection occurring in this room because of the normal temperature gradients, and that natural convection is enough to make sure to keep this atmosphere in here fairly well mixed. In space, that doesn't happen. You don't have that natural convection, and there have been instances where crew members, especially on space station, which is a very large, complex vehicle, if they've been having to get down, put their head down in an equipment bay or back behind a rack where there's not a lot of active ventilation, all of a sudden as they're exhaling that CO2, the CO2 builds up right in front of their face, and they begin getting feeling some effects from that. And so it's very, very important for us to make sure that we maintain proper ventilation throughout a vehicle. We're always monitoring the cabin environment, making sure its constituency is proper. We detect and suppress fires. We need to collect, stabilize, store, and dispose of wastes, solid and liquid waste generated by the crew, and supply water. Regardless of mission duration, all those functions I've talked about need to be provided in some form or fashion, whether it's a short, 1-day trip up to space station, or a 180-day mission out to deep space. All of those types of functions need to be provided in some fashion. As you begin looking at long missions, though, some other functions may or may not become attractive. And what constitutes long is something that Molly Anderson will talk to you about when she gives her talk on architecture considerations. But among the functions that may begin to make sense in long duration missions include recycling oxygen, recycling water, and in the extreme, even producing some of your own food. And that all of these things, these types of functions are there not so much because they're necessary to keep the crew alive, but rather they're necessary to keep the consumable mass to a manageable level to allow the mission to become feasible. And there are many trades that need to go into deciding to what extent you want to do any one or all of those. And you'll be hearing more about that through the course of the rest of the presentations. That's all I had on overview before I get into the history review of how we've provided those functions in past missions. Are there any questions? Okay.
I do have a question. You don't deal at all with psychological needs or anything like that?
We don't. Myself and my colleagues as ECLSS designers don't deal with that. The medical folks at the Johnson Space Center deal with that quite a bit. In the design of our systems, we take into account a lot of what we call human factors types of considerations that contribute, among other things, to the physiological well-being of the crew. But in terms of establishing requirements to maintain their well-being or assessing their psychological well-being, things like that, that's not within the domain of what we call ECLSS.
Okay, so you're dealing with physiological needs and then interfacing with the medical and others to integrate it?
Correct.
Okay.
I thought that was your job.
I'm ready to go down in space.
Because what happens if somebody gets the flu, out of space and they're just totally, not able to do their job? How do you deal with that?
Well, from a mission perspective, crew is cross-trained, and so although the crew members tend to have their specialties, there is cross-training among crew members for critical related tasks. In terms of life support, one of the impacts to us is we have to make sure that as we're designing our systems, and we're designing our systems to accommodate all that stuff I showed on one of the first charts, all the stuff that comes off of a crew member. We don't design for just nominal. We have to make sure that if somebody has the flu or they're sneezing into the environment and releasing all those virus particles and stuff like that, that we have active measures in place within our system to try to minimize the propagation of that through the environment.
Say, Bob. Oh, I'm sorry.
Yep.
Was there...
Is it like a sterile environment over there?
Excuse me?
100% sterile environment?
Right.
Sterile.
Oh, sterile.
Yeah.
No,
No.
It's not a sterile environment. It would be impractical to make it a sterile environment. We try to just make it as healthful as we can afford to make it, and that theme comes through a lot. If you throw resources at a vehicle, you can probably achieve extremely high levels of purity, but there's always a trade in that. And I think, Larry, do you have a question?
Yeah, I was just going to ask you real quickly, Bob. The focus of this workshop has been space radiation, hazards, and now life support. So I guess the question, or what I'd like to comment for at least this group for you to comment on, is there anything in particular with dealing with galactic cosmic radiation and SPE events in these long-duration missions that has an impact on your life support system that you could foresee?
Putting aside the impact of that radiation on our systems themselves, the electronics, you heard that yesterday. It's not unique to ECLSS, but our electronics would have to be properly protected. The only impact I would see kind of that unique on our system would be if, given that environment, and I forget which top speaker yesterday I heard them mention this, given that environment, if you take the radiation environment and then you begin coupling it with a microgravity environment, you put all these stressors together on the crew, and that winds up putting the crew at a degree of stress level that then would require us on the ECLSS side to, I'm just throwing an example out, make sure that our water is even cleaner than it it had to be on space station, or that the air is even cleaner, then it's had to be on space station. Those might be some of the considerations. One of the things on space station, for example, I talked about carbon dioxide. Carbon dioxide concentrations on space station, we control them, but they tend to be, they run a little higher than they do here on the ground. They run, I probably shouldn't throw a number out, but 3 to 5 millimeters of mercury on space station. And there has been talk within the agency as we start thinking about some of these future missions and start thinking about some of those other stressors that the crew is going to have to be living with. Our life support system may be tasked to control that CO2 to a lower partial pressure than we're allowed to do on space station.
Bob, I'm thinking about a couple of situations on Earth where also the same functions have to be provided that you listed here. One is commercial aircraft.
Mm-hmm.
You know, I flew to Singapore this is the longest commercial flight. It's Newark, Singapore. It's like 18 hours and 50 minutes. It's unbelievable, nonstop. And you know, you've got water, you've got food, you've got air. So that's one. And then the other is maybe submarines.
Yep.
You know, on submarine crews. So what are some of the high-level similarities and differences?
High level, I'll take the aircraft first. High level similarity, closed environment. They have a much higher density of people than we have on space station anyways, on a small spacecraft. That wouldn't necessarily be the case. But the big difference that an aircraft has is they continue to bleed fresh air into the cabin. So it's not 100% turnover of the cabin atmosphere, but they're always bleeding in fresh air. On a submarine's a little closer analog to what we're doing, and we actually engage with our Navy counterparts quite a bit. But they have some of the unique things that they have that we don't have. If you look on the water side, they are immersed. They've got plentiful water. And so they don't have to go to the extremes we have to conserve water. They got plenty of power, the nuclear subs, and so they don't have to design their systems necessarily to be very power efficient. The Navy tends to like, you know, they outfit these subs with large crews, you know, 100 types of crew members, and they don't. You don't want to have crew members in a submarine for a long period of time with nothing to do, and so the Navy deliberately designs their systems to be tended by a human being. You know, you get a sailor whose job is to keep the oxygen generator running. Whereas on space station, we deliberately design our systems to be as non-crew dependent as possible. On space station, the crew are there to perform science, not to keep the oxygen generator alive and running. Those are some of the obvious things. Yep.
I was just wondering, seeing that it seems that, you know, a trip to Mars really would focus a lot on recycling the resources that you take with you. If NASA, in any part, tries to be involved with the recycling effort on Earth as a way to learn how to do it better in space.
Yeah, we definitely try to learn, and I think there's actually, I think it going two different ways. It's actually a bi-directional learning experience. There have been, and I don't have any details in my presentations, but there have been some technology innovations that have been developed for space that have found their way into water recycling efforts here on the ground. An example we often talk about is on the space shuttle, the space, without going into too much detail, the space shuttle water that's generated from the fuel cells has iodine added to it as a microbial control agent. And the device that was developed for the space shuttle to do that has actually, the material that's been used to do that has actually found its way into some humanitarian water purification systems that have been deployed to Iraq and Pakistan, remote villages, earthquake relief type of humanitarian efforts to be able to provide safe drinking water for those types of environments. And then we've taken on the reverse side, and you'll probably hear some of this in the water talk. There's been a lot of work over the last decade or more on desalination systems, large-scale desalination systems to produce municipal water supply. And some of those membranes, some of those reverse osmosis membranes that have been developed and utilized there, we've been looking at for spacecraft applications. Mm-hmm.
I know that NASA uses a lot of machinery in order to recycle, the materials necessary. How much has NASA looked into using biological ways of recycling, for instance, using bacterial digesters or
in recent years, not much, and that's mostly been budget driven. You'll hear some of that tomorrow when Ray Wheeler talks, but back in the 80s, 90s, there was probably not what I would call a healthy NASA-funded research effort, but there was a sustained level for some time, but in the last decade or so, that's kind of fallen off. Anything else? Okay, so how has NASA and others gone about providing these functions in the past? If you look back over time, manned spacecraft, this is a collection of manned spacecraft back over the years. You're probably, hopefully familiar with most of these. Mercury, that was a one-person capsule. Its missions were very short duration. The first one was 5 minutes. The longest was 34 hours. Our country was using that back in the early 60s, 1961 to 63. About the same time, the Russians had their Vostok, later the Voskhod capsule. That also was a one-person capsule. Its missions ranged from a little over an hour to 119 hours. Again, that's what the Russians were using in the 61-63 time frame. From there, from the Mercury program, we went to Gemini. That was a two-person capsule. Those missions were a little longer in duration, the longest one being 330 hours. That Gemini program flew from 65 to 66. The Russians came along, followed up their Vostok and Voskhod vehicle with the Soyuz capsule. That's been a real workhorse for them. It's a three-person capsule. It can support the three persons for up to 10 days. That was first put in service by the Russians in 1967 and continues in service today. They've had 10 or so variants of that Soyuz capsule, but the basic capsule design has been a real success for them. They continue to use it. For us, we went from Gemini to Apollo, the command and service modules. Those modules could support three persons. Again, the mission durations there were in hundreds of hours. We used those from 68 to 75 in conjunction with the command and service modules, the Apollo lunar module, lunar excursion module, you'll sometimes see it referred to. That had two-person capacity. Its mission duration, while separate from the command and service modules, it was required to support those crew for about 1 to 3 days. It was used in 68 to 72. And then finally, Space Shuttle Orbiter, human capacity, and again, it's kind of varied by mission, but in general, a typical crew complement was about 7 crew members. Its typical mission durations were in the 10 to 15 days, and it ran for 30 years, as you all know.
Has your group been collaborating or advising any of the commercial crew spacecraft?
Yeah, the NASA has, you're probably aware, NASA is sponsoring a portion of the work being done by some of the commercial crew partners, SpaceX, Sierra Nevada, Blue Origin, and I'm brain farting the last one. SpaceX, Blue Origin, Boeing. Yeah, Boeing. The roles and responsibilities there are different than they've traditionally been. We are there as advisors, depending on the contractor, depending on what their interests are, depending on their desire and needs for advice. It kind of varies by contractors. In some cases where the contractors would like some very specific contribution from NASA, that's worked through Space Act agreements. But in general, what we're trying to do is take the accumulated knowledge we've gained from these experiences and help make that knowledge available to the commercial guys as they request it. Space stations, on the other hand, fewer. There have been fewer of them, obviously, than there have been for spacecraft. The United States' first space station was Skylab. It was actually put together from spare Saturn V parts. The space station, the main space station module, was actually a repurposed Saturn V upper stage that they actually re-outfitted to become a orbiting laboratory. Spacelab was able to support 3 persons. There were 3 separate Skylab missions executed in the early 70s. The shortest mission was for 28 days. The longest mission was for 84 days. After the 74 mission, Skylab wound up deorbiting, I forget which year it was, 75, 76, something like that. The Russians had a series of space stations they called their Salyut space stations. Numbers 1, 3, 4, 5, 6, and 7 are actually occupied for some periods of time by humans. They had, I think, Salyut number 2 had a failure, never was occupied. That's why you see the missing number there. But these Salyut space stations could also support 3 persons. They were periodically visited by crew. The shortest visit was 23 days. The longest visit was 183 days. And those missions spanned a little over a decade, from 1971 to 1982. The Russians followed their Salyut program with their space station Mir program. That was also capable of supporting 3 persons. The big difference there is they were able to keep the Mir space station, by and large, continuously occupied rather than having crews come and go and leaving it untended in between. It was continuously occupied and was in service from 86 to 2001. And now we have the International Space Station. It's a collaboration between the United States, Russia, Europeans, Japanese, Canadians. Its human capacity is 6 persons. It too has been continuously manned since 1998. Current plans are to continue keeping it in operation through 2020. There is some planning looking at what can we possibly do. What would it take to extend that operation out to 2028? So those are the vehicles and those are the space stations that have flown.
Quick question. The number 3, crew of 3, shows up an awful lot. Is there a reason why a crew of 3? Is it because everyone sleeps 8 hours and they can take turns? Is it because when there's a contentious decision to make, you need a
I think it's more of that. I think it's a balance, and Charlie may have something to say about this, but I think there's group dynamics involved. I think it's a division of work. How much work is required. On space station, it's not so much trying to get 24-hour coverage because the crew sleeps together, and I think that was typical of the other missions as well. And the larger crew you have, the more resources you need. So there's a natural tendency to try to get by with the minimum number that you can succeed the mission on. But I don't know if Charlie has anything else to offer.
I don't know. I don't know if there's anything magic about it, although the earliest mission that had 3 was Apollo, and that was clearly for the lunar orbit rendezvous, to have someone in the service module when the crew landed in the LEM and be up there. But I do not know if it's a magic number. Of course, the space shuttle has 7. The Orion was hoping for 6. I think SpaceX is looking at 7, and so. But I think a lot of it is going to be constrained by the size of the vehicle.
Yeah.
And so Orion may have been a little too large. And so we have to find, I think, that optimum number, in my humble opinion, is to get the people that have the ability that have multiple disciplines covered and can do several things besides just pilots. Have a medical doctor like Lee Morin that's also computationally he's a wizard and he's an engineer, and a Don Pettit that can build anything that you want up there. But
Okay.
I think Larry has something.
And just one comment on our architectural work. One thing to consider as we go beyond low Earth orbit, what station has allowed us to do, we've accumulated a number of international partners. And so on some of these future missions, even our crew size is dictated a lot in terms of like a crew of 6 or 7, based upon allowing all the partners to be able to send a crew member and participate too. So some of that's a factor as well.
And I can probably say a little bit about the Russian side. They're with a crew of 3, because they wanted to be the first nation to send a crew into orbit. So Voskhod was actually the same geometry as Vostok, which was designed for 1 person. They tried to manage to fit 3 people in there, but at the expense of not having a pressurized suit on. So 2 wasn't good enough. They had to go to 3.
So it was prestige.
Driven
First,
yeah. And then Soyuz evolved from the design of Voskhod.
But of course, politics never plays into it anymore. So.
I was wondering, what are some of the factors that help you decide the lifetime of the spacecraft?
That depends a lot on what the mission, predominantly on what the mission objectives are. If the mission is to go to a destination and then come back, and that is the mission, then orbital mechanics and space transportation capabilities dictate that.
For instance, a space station, how would you go about deciding? Because this is like one of them is like the international one has been operating since 1998.
Well, it's part of it's mostly because you've got a number of objectives that you're trying to use. It's a national asset that's being used for science. It's being used to prepare ourselves for exploration, so using it as a test bed. It's basically making, now that the investment has been made to develop it, the rationale is, okay, to how long can we afford to keep it in operation to be able to perform the science and perform the preparation for exploration. Any other questions? Okay, so how was ECLSS provided in all those missions? Now, I'll probably go through some of these charts fairly quickly, because I think you'll hear a lot of this in some of the follow-on speakers, but this will give you a flavor for how we went about it. I'm going to first, for the next 6 or 8 charts, talk about spacecraft, and then we'll talk about the space stations. In general, the spacecraft atmosphere conditions throughout the Russian program, their atmospheres were Earth-like, Earth-like 14.7 psi, 21% oxygen. U.S. history is mixed. In the earliest days on Mercury, Gemini, and Apollo, those vehicles were actually operated at 5 psi, substantially below atmospheric pressure, and at 100% oxygen. And that pressure was driven predominantly by EVA requirements. The EVA was a low pressure suit, and in order to protect the crew, either when they were preparing to go to EVA or in the event of emergency, in order to protect them from the bends, the decision was to run those vehicles at 100% oxygen and reduced pressure. Once we had the orbiter was outfitted with an airlock, and the nominal cabin pressure for the orbiter was 14.7, 21% oxygen, again, Earth-like type conditions. In preparation for EVA, though, the orbiter did have the capability for its cabin pressure to go down to 10.2 psi with an elevated oxygen concentration. When you go down in total pressure, you have to increase the concentration of oxygen to be able to maintain the minimum partial pressure of oxygen you need to drive oxygen across the lungs. So as we reduce pressure, you got to boost the concentration of oxygen in there to keep that partial pressure of oxygen below or above the minimum required for physiology. CO2 removal in spacecraft was predominantly expendable devices, lithium hydroxide or potassium hydroxide canisters. CO2 reacts with both of those to perform carbonates. Once the carbonates are formed, the material is expended. Very, very safe, very reliable, very predictable type of device. Works well in short duration spacecraft, but not so well when you start looking at some of the longer duration missions that we're talking about a little later. Oxygen generation. In the U.S., for these short duration missions, we didn't actually generate oxygen. We brought the oxygen that we needed with us. The Russians actually produced oxygen from potassium superoxide. They reacted, if you take potassium superoxide, react it with water, you produce oxygen and KOH. Trace contaminant control. In both programs, basically used activated charcoal and filters to maintain cabin cleanliness relative to trace contaminants. The orbiter added a catalytic oxidizer for carbon monoxide control and hydrogen reduction. Source for hydrogen, humans are a little bit of a source for hydrogen, but also in the orbiter, with the orbiter fuel cell system, there is potential for getting hydrogen into the cabin environment. Atmosphere monitoring. Russians generally in their spacecraft just focused on oxygen and CO2 gases with dedicated analyzers. In the U.S. and the Gemini program, we didn't do any atmosphere monitoring. In Mercury, we added a CO2 sensor. And orbiter went a little beyond that and added oxygen monitoring and relative humidity monitoring to the monitoring suite. Gas storage, I mentioned the Russians generated their oxygen rather than storing their oxygen, but they did have some small emergency tanks to use as a backup if needed. In the U.S. program, Mercury brought the oxygen they needed is in dedicated gaseous oxygen tanks. In Gemini, Apollo, and the orbiter, those vehicles used oxygen hydrogen fuel cells, and to get their energy, and to feed those fuel cells, the vehicles were loaded with cryogenic oxygen. Since there was cryogenic oxygen on board the vehicle, it made sense for ECLSS to tap into that, and so that's where the oxygen came from for those vehicles.
Hey Bob, can you just briefly talk about why the relative humidity monitoring?
That would be a good question for Hank. honestly don't know what the rationale was for
I
adding
think
that.
it may have had something to do with the LIO for the optimization of.
Yeah, one of the I touched on it a little bit, that reaction with lithium hydroxide when you're scrubbing CO2 out of the atmosphere, that reaction is dependent on the presence of water vapor. I think I have it on a later chart. You need water vapor to react with the LiO first to form a hydrate of lithium hydroxide, and then that reacts with CO2. And then as you get that reaction, there's actually water released. So, Charlie, you might be right. It might have been related to getting better optimization of the lithium hydroxide system.
Did the Russians do anything with, so in the previous O2 generation, did they do anything with the potassium hydroxide? Or did they just leave that as a byproduct and this?
Yeah, the question is, did the Russians do anything with the potassium hydroxide that was formed?
Right.
The answer is no. Not that I'm aware of.
So they just, so what's the advantage?
It was inexpendable.
So, sorry, so if it's the same weight, not the same weight, but what's the advantage of having that O2 generation where you can just bring more oxygen with you in terms of mass?
On the Russian side, I believe, and I think I got this on a previous chart, didn't show up on this chart, what the Russians were doing is they were taking water that they were condensing out of the cabin atmosphere, and they were using that to react with that potassium superoxide to produce their oxygen, and forming potassium hydroxide as a byproduct.
And they're just throwing it out?
So in effect, they were actually using their humidity condensate to help generate the oxygen by reacting it with superoxide.
Could that potassium hydroxide not then be used for carbon dioxide absorption?
The KOH? It could.
But they didn't use it like that?
Not that I'm aware of. Okay. For temperature and humidity control, the Russians, in their early vehicles, they flowed their air through a condensing heat exchanger. The water was collected on a silica gel. Downstream of the silica gel is where they had their lithium hydroxide and activated charcoal air purification system. Absorbing water on silica gel, that's another expendable type of approach. Once you've absorbed, in this case, water on that silica gel, they did not try to recover that water and do anything with it. On Soyuz, they also flowed their air through a condensing heat exchanger, but rather than using silica gel, they actually used water collected on porous wicks to gather that water and then be able to feed that to that KO2 oxygen generator. One of the unique things about microgravity is, unlike your home air conditioner at home, where the humidity condensate that's formed on the cooling coils, at home you have a drip pan and all that water separates itself from the cooling coils and drains away because of gravity. When you're in a microgravity environment, that doesn't happen, and so you have to compensate. You have to manage the flow of that fluid away from your cooling surface. And typically, in some of these early emissions, the approach was to take advantage of capillary forces to basically wick water away from the cooling surfaces. So you'll see things like porous wicks and sponge water separators in some of these early vehicles, trying to take advantage of surface tension forces to facilitate the movement of water from one location to another location. Mercury condensing heat exchanger with again a sponge water separator, same kind of thing on Gemini Apollo, except they went from a sponge water separator to a metallic wick separator. Most likely, I'm speculating here for reliability reasons.
I'm just curious because you mentioned about the porous wicks for capillary action. Will the chromatography work the same way over there?
Yeah, well, it's all the same kind of physical phenomena. You can I think a metal wick to me is a form of chromatograph. But yeah, it's all taking advantage of capillary forces. This is not particularly an ECLS thing, but capillary surface forces are also used in some propellant tanks. If you have a liquid propellant on a vehicle that's you're trying to draw propellant out of in a microgravity environment, a lot of those tanks use surface coatings and very unique geometries in the tank to kind of gather that water, bring that water to the walls of the tank, and then direct it towards an outlet of the tank where it can be drawn out. So capillary forces play a dominant role in managing fluids in a number of spacecraft systems, not just ECLS. In terms of water quality, these spacecraft, by and large, just had one type of water, generally called potable water. When we get to space station, you'll see there was a little more variety in the kinds of water that were made available. And in general, the short duration spacecraft were, once the water was loaded on orbit, loaded on the ground and launched, there was no on-orbit monitoring of the water quality once it was on orbit. Again, getting back to microgravity, when you store water in a tank, if you're not using capillary type forces, you have to somehow get that water out of the tank. Typically, what you see used are positive displacement types of tanks, where you either have a collapsible bladder or a collapsible accordion-like bellows of some sort that will expand and contract as the water, as the inventory of water changes in that tank. For water system microbial control, the Russians, since day one, have used silver ions as their biocide. They've used that quite successfully. On the U.S. side, in the Mercury program, they basically just filled the water tank up with KSC municipal water supplies. Once we got to Gemini Apollo, got a little more elegant, used chlorinated ground processed water. And then Apollo, the lunar module and orbiter, the space shuttle orbiter, was where the U.S. first began using iodine as a microbial biocide, and we're continuing to use that on space station. One of the lessons learned, I don't want to get ahead of myself, but on space station, we now on the Russian side of the space station, they're using silver as their biocide. We're using iodine on our side, and it winds up creating a not a very user-friendly combined system, because you wind up you cannot mix iodine and silver without causing silver iodide precipitation, which if we had to start over again, we wouldn't have designed the system that way, but we are where we are. Fecal and urine handling. This is another area where gravity really helps us out a lot here on the Earth, but we have to compensate for its lack in gravity. In general, since we don't have gravity to aid in the separation of the wastes from our bodies, we generally use air as a substitute. By focusing airflow in appropriate strategic locations and directions, we can facilitate the removal and separation of the wastes from us. In Mercury, those missions were really short, and the crew members either went before they left home, or basically wore diapers. Gemini and Apollo, those missions were longer. The fecal collection was very rudimentary, and it was called an Apollo bag, basically taped to your butt, and that's where you went. The orbiter, we did a little better than that, not quite as rudimentary, but again, and you'll see some pictures of it in a minute, where we began using air to properly direct and facilitate the separation of waste from the body.
Wasn't there a story about Alan Shepard that there was a big delay in his flight, and they hadn't planned for him to need to?
Oh yeah. Yeah.
I don't know the whole story. Do you know about that?
I don't know the whole story other than what I've seen in the movies, and he's sitting there on the pad and wound up having to go, and so he went. Fire suppression, and these charts were put together by Hank. Hank didn't have any knowledge of what the Russians did on their spacecraft for fire suppressants. I'm pretty sure, although I probably shouldn't quote this, but I think they use water-based suppressors. On the U.S. side, in Mercury and Gemini, in those missions, the crew members were in their suits. So if there ever were a fire, the plan was for them to go visors down in their suits and just depress the cabin. Once you depress the cabin, get rid of the oxygen, the fire goes out. And you also, by doing that, you're venting any type of smoke or other noxious chemicals that were resulting from that fire. So that was the approach back then. In Apollo, so when the crews were not always in their suits, we had to come up with something other than depressing the cabin. So Apollo used the water spray and foam fire suppressant. On the orbiter, we used Halon 1301. One of the interesting asides about that choice, not just its availability, but when the orbiter was docking with the space station, and we'll talk about this in a minute, space station had a catalytic oxidizer as part of its trace contaminant control system. If halon ever got into that trace contaminant, that catalytic oxidizer, it would start forming some acid gases that would be nasty stuff. So we wound up, and this is one of those architectural kind of considerations, we wound up having to establish some strict flight rules to make sure that when the shuttle was at the space station, any inadvertent release of halon would not propagate over into the space station and contaminate the catalytic oxidizer. Smoke detection, humans are actually remarkably good at detecting fire. And so we always make use of the crew to smell what we can't quite detect. But the orbiter did add an ionization smoke detector to the system. All right, that's spacecraft. Now we'll talk space stations. Again, these are now the longer duration vehicles.
Do we share our system designs with the Russians, and do they share their designs with us?
That's a really good question. Back before the Mir program, we had our separate programs. We tried to keep ourselves, secret. But physics is physics, chemistry is chemistry, and one of the things that I kind of found satisfying is when I came on board with NASA in 1985, we were going through technology trade studies and trying to figure out how to perform all these life support functions, and we came up with our selected ways of doing it. Meanwhile, the Russians were doing the same over on their side for the Russians, and once we became partners and we began exchanging information for the Mir program and then for International Space Station, lo and behold, the kinds of technologies we wound up using were similar. There was differences in the engineering implementation of them. Some of the technologies were a little different, but by and large, there was more similarity than differences. And again, I think that's driven by chemistry and physics.
Bob, can I comment on that? Yeah, Jennifer, when I was training in Russia, what I loved was that the trainers there, because when we go up to space station, the Russian capsule is our lifeboat. And so all the U.S. and the internationals have to train on Russian systems. And so you go over there, you pass their tests, and their trainers are very, very knowledgeable, not only in the operation of the equipment, but really in the engineering and the physics of the equipment. And so what I love to do was look at how the Russians engineer and design systems from a totally different point of view, like I was talking about, to look at creativity, how they solve very similar problems that we're solving, like Bob said, but slightly differently. And so I was, and so you can learn a lot from them. And a lot of what they do is very simple. You've heard a couple of people comment about that. They look for the simple approach. And we could talk about that a little bit more when we're talking about designs and coming up with innovative solutions to problems, how you could merge those ideas.
Space stations, CO2 removal, the Russians, even on their Salyut missions, they were using expendable lithium hydroxide canisters for CO2 removal. Once they got to Mir and their portion of the ISS, they use regenerable silica gel desiccant beds with 3 molecular sieve beds, basically absorb water vapor. And on silica gel, you absorb CO2 on molecular sieves. The CO2 is vented overboard. The water vapor is picked back up off the silica gel by recycling your purified air back through the silica gel. The reason they do that is they want that water vapor back into the cabin atmosphere so they can condense it and use that humidity condensate as part of their water recycling system. So they're trying to conserve water with doing that. You'll hear more about this in later today, but the reason there's silica gel in that system is molecular sieves, which is really what you're wanting to use for CO2 removal, also have a high affinity for water. So in order for you to get the CO2 removal capacity you need, you have to first remove the water so that you're able to control your CO2. On Skylab, we also use a molecular sieve for CO2 and humidity removal. We just dump the humidity overboard rather than trying to recuperate it. And again, that was because Skylab was launched on Saturn V vehicle. We had plenty of launch capacity. Skylab vehicle was outfitted with 10 600-pound water tanks on board, and so they had more water than they needed to fulfill those missions, so they didn't care about venting their humidity condensate overboard. Once we got to space station, though, we didn't have that luxury, so we, like the Russians, use a molecular sieve with desiccant beds up front for water save. Gas recovery, this relates to trying to recover oxygen from your CO2. The Russians are not doing anything on, did not do anything on Mir and are not doing anything in that regard on space station now. We also didn't do anything relative to that on Skylab, but on space station we have something called a Sabatier reactor. Rather than throwing that CO2 overboard, we are reacting it with hydrogen, which we're getting from our oxygen generator, to produce methane and water. Water is what we're after. That's the commodity we want. We use that water and throw away methane. So rather than throwing away CO2, which is close to 3/4 oxygen, we're throwing away methane instead. Oxygen generator generation, again, on Salyut, the Russians did not generate any oxygen. They brought all they needed from the ground. On Mir and ISS, they're using water electrolysis plus, as an emergency backup, solid fuel oxygen generators. Interesting story here, there was actually a serious fire on board the Mir with one of their solid fuel oxygen generators. It actually turned into quite a hairy event. And, Charlie can probably tell you more about that if you're interested. On the U.S. Skylab, we didn't generate any oxygen, but on the ISS, we also do water electrolysis. Getting to the question about similarities, you see we're both using water electrolysis. Same basic physics, however, the engineering implementation is actually quite different. The Russians use an electrolysis system that circulates a liquid potassium hydroxide solution as an electrolyte. We use in ours a solid polymer electrolyte system, and ours comes to us through the Navy heritage. So there's a linkage there to the Navy. Trace contaminant control, activated charcoal filters.
On the gas, were you going to talk a little bit about how we do EVAs now as opposed to how we going through the airlock and letting that air go, as opposed to now on the space station we basically create a vacuum in there and bring that air back into the.
Yeah, I don't have any charts on that, but what Charlie's asking about is we're always trying to preserve our gases as much as possible, particularly when we do EVA and go out through an airlock. You've got two basic choices. You either vent all the gas in the airlock out to deep space, in which case you've lost that gas and would have to replenish that, or you can try to scavenge that gas, try to pump that airlock gas either into your cabin if you've got the volume to accumulate, or into some interim storage tank, so that you can then use that gas at the end of the EVA to help repress that airlock. Trace contaminant control, in the absence of time, I'll just say in general we use activate charcoal and filters. Atmosphere composition, again, the Russians in the Mir and early space stations were Earth-like types of conditions. In Skylab, we ran Skylab at 5 psi. However, we knocked the oxygen concentration down from 100% to 72%. Space station, again, is Earth-like with EVA prep at 10.2. Monitoring, you'll see the list of devices there. I'm going to skip through this kind of quick. Gas storage, we talked about the Russians generating their oxygen chemically from perchlorates. They also maintain a supply of compressed air as emergency backup. Or on the Salyut vehicle, excuse me. And then on station, they have small 22-liter portable tanks for oxygen or air. And they also have these oxygen, what we call oxygen candles, to chemically produce oxygen if they need an emergency. In Skylab, again, we had a nice large launch vehicle, so we were able to launch a lot of what we needed in compressed tanks. We did scavenge some cryo oxygen off of the Apollo command module while it was there. Space station did the same kind of thing. While the orbiter was flying, we did have the luxury of being able to scavenge oxygen from the orbiter cryo tanks. We don't have that luxury now, and so there are some provisions in place to replenish oxygen supplies from the ground with compressed oxygen tanks. Space station's also looking at other ways to do that. Cabin ventilation, multiple cabin fans throughout the vehicle, cabin temperature and humidity control, using condensing heat exchangers as before. Humidity separation, we've kind of gotten away from capillary type devices and going with rotary centrifugal type devices. For water supply quality, I mentioned at least on the Russian side of the space station, they actually maintain 3 different grades of water now on space station. Potable water, which is safe for crew consumption, hygiene water, which is safe for crew use but not consumption, and then electrolysis grade water, which they use to generate their oxygen. And then on the U.S. side, we treat everything to a potable water standard.
On the Russian side, their urine, processed urine, goes into hygiene, and ours goes into drinking water. Is that correct?
The Russians don't have a urine processor, so what they do is they carry their urine in a tank over to the U.S. side, and we process it over there.
And did you want to say, because there was some issues with the urine processing assembly that we had talked about, where there were some problems?
Yeah, one of the interesting things, I don't think I got to urine processing yet, but we are processing urine on space station. One of the things we didn't take proper account into, and you heard it yesterday, I forget who the speaker was, but one of the speakers late yesterday afternoon was talking about bone loss, calcium, release of calcium from bones. Where does that calcium come out? Well, going back to that very first chart, it comes out mostly in the urine. We were back in the 80s, 70s, well, even dating back to the 70s, but particularly in the 80s and early 90s when we were developing our space station urine processor, We thought we were being smart in collecting, hundreds and hundreds of gallons from ourselves down on the ground and processing that through our urine processor, through a distillation process. We came to, with very high confidence, came to the conclusion that we could recover up to 92% of the water from urine before the salts that were left behind in the concentrated brine began precipitating out. So being the conservative engineers that we thought we were, we said, well, we know we can get to 92% recovery. When we operate the space station system, let's just go to 85%. That'll give us, 5 to 7% margin of error. Well, lo and behold, we flew the urine processor, started processing urine on orbit, and started precipitating out at 65 to 70%. And saying, well, what's going on? And that failed the system. What we didn't account for is that astronaut urine is much higher calcium concentration than our urine on the ground. Because we were starting at a higher concentration, we reached the solubility limit much sooner in our processing cycle. We formed solid precipitates. So one of those, it's kind of a microgravity physiological effect that influenced our system. And right now we're operating at 70% water recovery on our urine processor, trying to figure out a way to get that calcium out of there before we distill it, so we can get back to where we'd like to be at 85%.
Quick question on the electrolysis grade water. Is that actually, in a sense, purer than potable water? Because electrolysis means you're splitting the water into oxygen and hydrogen with electricity. The question is, that's not. So is that in a sense purer than potable water, but it's not fit?
It does not have. The Russians actually add, once they purify their water, they add minerals to it for the potable water, because that's kind of a cultural thing. And this gets back to there's a debate, I'll call it, between the U.S. and Russian physiologists about, is it better to what extent do you need to get your mineral intake in your body through your drinking water and your food versus as a vitamin supplement enough. The Russians feel very strongly that you need to have some amount of mineral consumption with your water. I think that's also a kind of a social thing. If you go to Russia, they drink a lot of mineral water. That's what they like. They also add silver, and neither minerals nor silver are friendly to electrolysis systems. So basically their electrolysis water is purified water that it does not have the silver or the minerals added to it.
Hey Bob, just another, while we're talking about water, I was at Marshall when they were having problems with the active cooling loops that used water. And, little known fact, you have to maintain that water in the active control cooling loops inside that they're using water for cooling to a very high purity. Yep. And you have to monitor the chemical balance in there, because it could potentially start forming algae or the
another problem we ran into that Charlie's alluding to, we have, and I haven't talked about it here, but space station has active cooling loops running throughout the station to cool electronics and whatnot. Because space station is something that's assembled on orbit with elements and you're always changing racks out, that system has a number of flex lines located throughout the system. Those flex lines are Teflon based, and so they are permeable to gases. I mentioned that the space station cabin atmosphere tends to have a higher CO2 concentration in it than down here on Earth. One of the problems we ran into on space station is the chemistry of the coolant loops started going haywire. The pH started dropping. It was causing some corrosion problems and a real headache for the thermal guys. The reason for that is because of the higher concentration of CO2 in the cabin environment, the diffusion of CO2 into the cooling loop was much higher than we expected. That CO2 going into solution dropped the pH of the solution, causing the problem. So again, one of those, that's more of a closed environment, unique kind of problem that we ran into that we had to work our way through. But yeah, Charlie's right. It was a real big headache. And I think I'm going to I got a couple more charts I'll hit. Water recovery, I just alluded to this. On the Russians side of the station, they recycle humidity condensate. On the U.S. side of the space station, we recycle humidity condensate and urine. You'll hear more about that later. Tanks we talked about, positive displacement tanks, silver I talked about. Again, on space station, we got 2 biocides that aren't mutually compatible. Fecal and urine handling, again, we're using air as a substitute for gravity to direct where the waste goes. Smoke detection, on Mir and Space Station, the Russians use optical smoke detectors. On Skylab, we use photoelectric detectors. Fire suppressants. On Skylab, we use something called the aqueous gel extinguishers in like a foam configuration. On Space Station, we're using portable CO2 extinguishers. One of the things we like about CO2 is you can, unlike halon, it's toxic, like halon, for different reasons, but we can remove it. We have CO2 removal capability on the vehicle, so if you ever did have a release of CO2, you have the capability to get it back out of the atmosphere. CO2 works good in a large space station. It doesn't work so good in a small capsule because now you're in a much smaller environment, and the amount of CO2 you have to have in that extinguisher, if it were to release into the environment, results in a much higher, potentially toxic level of CO2 in your cabin environment. So what you pick for a fire suppressant actually is influenced by how large an environment you have to work with. And then I think I'm going to call it quits there. I'll just let you know that in this presentation, which I think you're going to have online, there's a lot of more detailed information. You can see some schematics and nifty pictures of things in the orbiter and in space station. Show you what's in there, but you got pictures of space station equipment and stuff. So that's the. I guess I shouldn't. That's the space station, what we call the regenerative life support system. It's 2 racks make up the water recovery system. The 3rd rack makes up the oxygen generation system. This shows all the ins and outs from that. But basically what we're doing is we're getting urine and humidity condensate supplied to the system. The water goes round and round. It comes out there. It's potable water. Portion of the potable water also comes into our oxygen generation system, which produces oxygen and hydrogen. This is an early photo. This photo shows the oxygen system in its launch configuration. After the oxygen system was launched, this blank space that's located here was outfitted on orbit with that Sabatier CO2 reduction process I mentioned. So now, rather than venting hydrogen overboard, the hydrogen's coming up here to the Sabatier. It's being reacted with carbon dioxide to produce more water that we then feed into our water system.
Hey, Bob, could you maybe say a few words about the changes that resulted in ECLSS system due to the retirement of the shuttle, especially like fuel cell water use and some of that?
Yeah, when the shuttle, I mentioned when the shuttle was flying and docked to the station, we took advantage of the availability of cryo-oxygen boil-off, so we scavenged that, stored it on board. We also took advantage, as the orbiter was running its power system, the fuel cells were reacting hydrogen and oxygen to produce water and electricity. The orbiter used the electricity. We scavenged the water. The water was carried across the hatch, and that became a supplemental water supply for the crew to use. Now that the shuttle's not there, we don't have that supplemental water supply to make up for the losses we have elsewhere in the system. So we're now having to rely on deliberate launch of water on Progress ATV and HTV resupply vehicles.
Quick question. So these racks that we see here, do you have an exact replica of the ISS system at Marshall, so that if a failure occurs on orbit, you can replicate that failure and then come up with a fix?
We have a functionally equivalent, which means that we don't go to the expense of some of the more detailed packaging, the ruggedization, what I would as an example, we have the geometries of the beds, the length to diameter ratio of media, but not necessarily the weight optimized design of the bed structure. You know, those kind of differences. And then we also don't tend to package things closely because on the ground we need to be able to get in and fool around with stuff.
Another thing they do, Ollie, for instance, for the cooling, the cold plates, for instance, they have a set of cold plates that they use a principle called fleet leader that you're familiar with, where they're basically cycling these cold plates on the ground additional times ahead of the ones that are up there flying on space station to see if there are any potential problems that might arise. So they're burning those in and cycling them, putting them through the same number of cycles. So that's a different kind of a design approach to kind of understand what the life capabilities are and other potential problems, the unknown unknowns.
I'm familiar with that idea of from the F-18. You know, my work on the F-18, where we had a fatigue life test bed. You know, so we had, you know, the leading airplane in the fleet had maybe 800 hours on it, but the fatigue test article had 3,000. The problem was when you're stressing your test article, you're trying to be as you know, the load conditions and the conditions you put in, you're trying to be as realistic, but you're always off somehow, right? So the question then here is the functionally equivalent test bed that you guys have is in a 1G field,
yep.
and you're in microgravity with the real system. Does that cause any differences inside of these processing units?
Yeah, in those cases, we try to eliminate that to the extent possible. For probably the best example within our urine processor system, in urine processor in Iraq, oriented vertically, we have head pressures that we have to deal with on the ground. But on space, we don't have to. In space, we don't have to deal with that. So in our ground development unit of our urine processor, we take our hardware, and rather than orienting it vertically like it is in the rack, we orient it horizontally, and actually go to great effort to try to position the equipment to eliminate the head pressures to the extent we can between critical parts of the system.
Did you do value engineering studies to try to optimize in terms of sending these systems into space and recycling and all the complexities of this? How did you go through an optimization process to figure out what to do?
Our first criteria is we had to produce safe water. We had to do it in a microgravity environment. We had to deal with the wastes we were given. And so, honestly, I think looking back, our first criteria was making sure we got the performance we needed. And we need to be able to do it with enough reliability that we had confidence that when these systems were put into operational use, they would perform those functions and do it safely. We recognized that our systems were dependent on a number of expendables within the water system. There are expendable filtration beds. There are expendable particulate filters that have to be, once a system is operation, they have a finite life. You have to remove them from the system and replace them on orbit. Those are all conscious decisions. Interesting thing, back when we were developing this system, we were developing for a space station that was going to be resupplied with a space shuttle. So in that type of mission architecture, we accepted the fact that portions of our system were going to be expendable based. Then after the system was developed, shuttle gets retired, and now all of a sudden your value, in your words, of relying on expendables changes. Mm-hmm. And so we're having to deal with that. There's as we're looking ahead, and I think you'll hear this as a theme in some of the later presentation, we're learning a lot about how to operate these systems. And we're recognizing that although I don't have any metrics in this presentation about how much water they produce, but that water system has produced close to 24,000 pounds of water since it's been on orbit. The oxygen system's produced over 2,000 pounds of oxygen. Really paid for themselves mass-wise, but now as we're thinking about, okay, leaving low Earth orbit, going out to wherever, and not having that resupply chain, if you will, we're really challenging ourselves to understand where are the reliability shortcomings in these systems and what can we do to improve that reliability and get that high reliability we're going to need in order to take that next step without making such substantial changes in the technology that we're throwing away the heritage we're accumulating. And so it's a very tough balance. We want to make sure that we take advantage of the years and years of experience we're going to have with these systems before we go out to wherever we're going to go next. But at the same time, we recognize that we gotta make these things much more reliable than they've been so far.
Just a follow-on question. We were told earlier that it currently, I guess, costs about $10,000 per kilogram to send something up. And so you're balancing the cost of, at least now, the cost of resupply versus the cost of having sophisticated equipment there. And now going to Mars, it really changes, as I think you're pointing out, the value engineering of it because you have no resupply. So what is your waste
I don't know
rate?
what the cost per pound is going to be, but it will always be very expensive. I think we can count on that. And so I think you'll see in Molly's presentation, I think she's going to introduce the concept of break-even analysis and how do we do that. Typically we do it on a mass basis, not so much from a dollar basis, but it's one of the things we pay attention to.
Two questions. The Saboteur's reaction, wouldn't it require a large amount of energy to continually power that? And then the second question is, with hydrogen and carbon dioxide mix, I'm assuming that you have solid carbon. What would you do with that carbon?
The first question, Sabatier, once it's up and running, is actually a exothermic process. And so it's actually fairly energy efficient or doesn't require much energy. And the second thing about formation of carbon, in a Sabatier, we don't go all the way to carbon. We're producing methane in water. One of the shortcomings of that is if you look at the stoichiometry, it limits us to recovering no more than 50% of the oxygen that's available to us in carbon dioxide. Looking beyond space station and trying to close the oxygen loop, if you will, further, there are approaches that will allow us to either take that methane and recover hydrogen from it so we can react with more carbon dioxide, or go straight to solid carbon directly. That gives you the potential to recover potentially 100% of your oxygen, but just like you say, you're now having to deal with the difficulties of producing solid carbon, which is soot, and dealing with that.
Yeah, we're going to have to. Can I ask one more question? It's a highly inappropriate. But, so we have. There's some of you are chemistry teachers, right? Teach chemistry. You are. So your chemistry lab in the high school. If you wanted to do some experimentation in high school with some of these, you couldn't do all of it, but you could pick a couple of these processes. We're talking about maybe doing a lab here, like a university-based ECLSS lab. This looks really scary. So just how many millions of dollars, how expensive was it to create the system and to build a system like this versus a lower grade or a simpler one?
You're looking at about $300 million in that picture. But I could get you a deal. But in all seriousness, the chemistry and the physics you can simulate fairly easy. You can do a urine processor in a rotary flask on a bench top. You can distill urine and condense the distillate and do that kind of stuff. So it's manageable.
What I did in my class is I know that amount required by a single person in the ISS space station around 834 grams of oxygen per day. So I asked my students to do electrolysis, 30% potassium hydroxide solution. they put the electrode and they collected the oxygen. They measured the volume and they were comparing how much they are producing in class per a certain amount of time when current flows through it. And we did that in class.
Okay, we're gonna have to speed things along because we do want to have a break. But I want to thank Bob.
Sure.
Unbelievable.